Lecture 1.18 is about the derivation of gas law equations. So what we're going to do is we're going to look at all the factors that gases are affected by. We're going to look at its volume, its temperature, its pressure, and how many particles, gas molecules, are involved in the gas. And these four variables collectively describe gas behavior. Okay, so we're trying to basically take gases and quantify how they'll change with all of these different variables. So a gas is affected by how much space it's in, how fast it moves, the pressure it's under, and how many of the gas molecules the gases have themselves. So we're going to combine these four into two basic equations that'll take us through most of the gas laws. All right, so let's first look at some variables here. Let's look at volume and how it relates proportionately to, let's say, temperature. Now this is a proportion sign. It means as one goes up, the other one goes up. As one goes down, the other one goes down. So this is called Charles's law. And this relates volume and temperature. So volume and temperature, are proportionate to each other as long as a couple of variables stay constant. We're going to go back to what those are, but let's take a look at a movie for Charles's law, temperature and volume. Okay, this should look really familiar to you, and here we go.
As the frequency of collisions with the walls of the balloon decreases, the volume.
Let's start that from scratch, and here we go.
Gaseous atoms collide with the sides of a balloon, exerting a pressure that opposes atmospheric pressure. If we decrease the temperature of the balloon by immersing it in liquid nitrogen, the kinetic energy decreases.
So as temperature decreases,
as the frequency of collisions with the walls of the balloon decreases, the volume decreases.
Couldn't say it any better. Okay, so as temperature decreases, because it moves slower, it takes up less space. Okay, now that's only true, my friends, if, in fact, we have some things stay constant. If the number of gas molecules stay constant. Now we're going to call that number n for number of particles. So if that stays constant, and as long as temperature stays constant, we've got ourselves, a relationship. So as long as the number of molecules stay constant and temperature stays constant. Now think with me, if I have a container that's movable, flexible, and I have gas molecules, if I lower the temperature, the balloon will deflate, as you can see, because the molecules don't need as much space. That's what we saw with liquid nitrogen demonstration I did in class. However, if I was to add gas molecules to this container, increase N as I did it, this would not deflate. And if I increase the temperature, this should be pressure, If I increase or change the pressure, like decrease the pressure, this could actually get bigger as I drop water on it. So the two variables that have to stay constant for this to work are the number of particles, we call N for number of particles. When I use the word mole for that, and pressure. There's the two things that have to stay constant. All right, so what is the other variable? Well, we have volume being proportionate with, moles, or this N number. This N number represents moles. It's a word that describes how many particles. Now that's only true, of course, when we have the other variables constant. Temperature has to stay constant, and pressure has to stay constant. And that should make some sense to you. Let's look at an animation of temperature, of the volume, and the number of moles. We call this Avogadro's law, so let's write that. Avogadro's law. And he stated that if you increase the number of particles, you're going to increase proportionately the volume. This is a proportionate sign. So let's look at a demonstration, or an animation, and here's one.
If the number of gas molecules in a container is doubled, with no change in the temperature or volume, the number of collisions between gas molecules and the container walls doubles, which translates into a doubling of pressure.
Okay, so clearly, if you add more particles to a container, again, keeping temperature and pressure constant, you're going to, in fact, increase the volume. Obviously, if you decrease the temperature while you're adding gas molecules, it won't happen. So you can see that these other variables have to stay constant. Okay, so we have another and final one that covers all the bases. Volume is proportionate to 1 over P. Now this is an inverse relationship. Notice 1 over P. For instance, if I was to increase the pressure on a gas, the denominator gets bigger, which means the overall value of this decreases. As one goes up, the other one goes down. It's an inverse relationship. This is called Boyle's law. Now the names aren't as important as the relationships. So Boyle's law, inverse relationship, and we're going to look specifically at these different variables. Now, of course, Boyle's law only works, okay, when we're dealing with what else is constant? Temperature is constant, and the number of moles. Okay, so let's play a video that shows volume and pressure. Okay, here we go.
A decrease in the volume of a gas sample results in an increase in pressure because the gas particles will hit the walls of the container more often.
Couldn't have said it any better myself. Okay, so of course, as the piston comes down, it makes the space smaller for the gas particles. Okay, the gas particles are going to collide more often. Okay, so of course, that only works if temperature is staying constant. Now, I have to remind you, a very important thing here. Temperatures in these gas laws have to be in Kelvin temperatures because we're dealing with gas behavior and we want to know the temperature, okay, that gives me an actual value of how much motion to a zero line. If you give me Celsius, think with me, put in a Celsius zero value in your equation that we're going to build, and we're going to get out zero numbers. Put a negative Celsius. What's negative motion? So we need an absolute value. And my friends, Kelvin is how we do that. We use Kelvin temperatures always. And that's going to come into some serious play as we do some more equations. So that's something to think about. We have to be in a positive scale that reflects how much motion. Celsius is not a positive scale that reflects how much motion, especially the negative numbers. Okay, so let's put these relationships together. Okay, and let's change our inks to do so. All right, let's do a little magenta here. So we've got volume is proportionate to temperature. Well, volume is also proportionate to moles, so I can put that next to each other. Volume is also 1 over P. So there's my basic relationship. Volume is proportionate to temperature in here. Now, this is a great relationship here, but it doesn't really help me. The problem here is that I don't want to know proportionally what happens. I want numbers. I want a quantitative value. So what we're going to do is we'll put them together. And we're going to take a step back before we do that. Okay, and I'm going to show you how we go from volume is proportionate to temperature to volume is equal to temperature. And let me show you what that's about. So we're going to put this away for now. And I'm going to change, edit undo. I'm going to change this proportionate sign to an equal sign. And I just did it again. All right, let's just get rid of this. Yeah, I did it. Okay, so I have my volume is proportionate to temperature when these are constant. Well, how about if I make it equal to temperature? And that's the number I can use. But that's when I times it by a constant. I'm going to call this K1. What is that constant? That constant, okay, is these two numbers multiplied together. So if you know what these two numbers are and you multiply them together, that's what K1 is. Now, you may say, I'm kind of confused. You're adding a constant. This is called a proportionality constant. Let's think with me for a second. Let's do a little thing here. Revenue is equal to, let's see something. I have 2 theaters. One theater has 100 seats. And another theater has 200 seats. And I want to do a relationship. I want to say revenue is proportionate to the seats. Right? Assuming that I sell out all my seats to every show in my theaters. So revenue is proportionate to seats. It's a proportionate side. It doesn't tell me how much I make, it just tells me it's proportionate. I'm going to have a proportionate value based on my seats. Okay, whatever that relationship is, I need a factor to tell me. How can I figure out exactly what my revenue is going to be? I know how many seats, and you probably figured this out, how about the price per seat? Once you have the price per the ticket, and I times a seat by the price, people, I exactly know what my revenue is, and this proportionality sign goes from being a proportionality sign to an equal sign. Notice what I did there. I took out the proportionate sign and added, okay, a constant. This could be the K. Okay, that's the price per seat. So I take my seats and times it by the price per seats, and that equals a number I can use, and that is how I get rid of my proportionality constant. That's how I get rid of my proportion, by adding a constant that takes it away. So just like over here, it was proportionate volume to temperature, but now I add the proportionality constant, and now I know I can use numbers now. This has to be a constant that I know of, and it's basically moles times P. Okay, so over here, volume is equal to N times K2. What's K2 equal to? Temperature times pressure. It's another proportionality constant that gives me the price per seat, so I actually know what the number is. And then I have volume equals, okay, 1 over P times another we'll call K3. What's K3 equal to? The temperature in Kelvin times the moles. Once you know those two values, we have those. And again, these are proportionality constant. They tell me the price per seat to change the proportion sign to an actual equal sign, to numbers I can actually use. Proportionality to revenue is great, but we want to know exactly how much we're making, and that's where the equal sign comes from, and we don't get that until we have that constant, which is like the price per seat. Okay, let's put this now equal relationships with our constants together. Okay, so let's put this all together, and volume is equal to temperature times moles over P times our what? Our constants. And this time it's K1 times K2 times K3. Okay? Now, we multiply all these K's together, we get a major proportionality constant called R. R is called the universal gas constant. What the heck is R? It is our proportionality constant. It is our price per seat. It helps us get equal signs. It's all these constants together. Okay, I'll explain in more detail what it is, but this is a proportionality constant. It helps us, basically gives us a constant value of how all these are interrelated. It's the fixing number that glues these concepts together. I'm going to give you a little example what that is in a second. Okay, so you put this together. Okay, and let's rewrite this. We get, all right, V, I'm just going to rewrite a little bit, N, okay, T, and here's our R, which is represents of all the constants together over P. Okay, now I'm going to write it one more time, so I'm going to get rid of some things here. In fact, I'm going to move it down. So I'm going to move it down. So I got my, let's just do this right here. Volume is equal to N, I want to put the R, T, over P. Again, our R comes from this. And then sometimes, for the most part, we rewrite it one more time. Put the P up to the top, so PV equals nRT. And this is something called the ideal gas law formula. That's its, formula. That is its formal name, okay? Pinky up. All right, now, I have a different name for this. I call this the static formula. How do I know when to use this formula? Very simple. I have one pressure, one volume, I know the moles, and I have temperature, of course, in Kelvin. Or excuse me, I have pressure, volume, moles, solve for temperature. Wow. If I have 3 of the 4 variables, I can solve for the other variables. Notice nothing is changing, so I call it the static equation. Okay, especially that idea of moles. But let's talk about R for a second. Since we have the ideal formula, what does R equal? R is equal to, think about this for a second, PV over NT. Change of y of a change of x. If I was to plot pressure times volume for a particular gas scenario and the moles times its temperature, keeping those constant, I get a straight line. Or I get a line, a linear relation between these variables. And guess what your slope is? Your slope is equal to r. So the slope, or the relationship, the linear relationship between pressure times volume and n is right there. Okay, change of y over change of x. Another way to think about how these things are. Now, more importantly, what's the value of r? R is a constant. You need to know its values or its units. We have a different couple of ways to look at it, as many different units, but we're going to use atmospheres, 1 atm. We're going to use volume in liters. And we're going to use moles is the word that tells us how many particles. And we're going to use temperature in Kelvin. I'm not going to really put 1 here. So the units are atmospheres, liters, mole, kelvins. That's the unit, okay? Kind of like the units you were using for specific heat. Now, what is R equal to? Well, using these units, it's 0.0821. All right, so the universal gas constant that you're going to be using initially, R is equal to 0.821 atmospheres, liters, mole, kelvins. Okay? And that tells you what units you have to be in to solve this equation. So when you have PV equals nRT, if you're using this R, and I'm only giving you this one, your units have to be in liters, atmospheres, of course in moles, and in kelvins for everything to cancel out. All right, we have one more, and I'm almost done. Okay, let's go back to PV equals nRT, our static equation, and let's just put this. Just going to rearrange it a little bit. PV over RT. Okay, let's get rid of the R. PV over T, I meant. That equals RT. Oh, Christmas in July. Sorry. End of the day. NR. So all I was trying to do is just move the T down. Okay. So this is, I'm just rearranging. So I'm algebraically putting the T on the bottom, and I have PV equals RN. Okay. Now, if PV over T equals RN, okay, universal gas constant moles, doesn't RN equal PV over T? This could be one scenario, and this could be a new scenario. So we're giving birth to a new equation here. If I knew the pressure and volume and temperature of a gas, and if its pressure changes, its temperature changes, could I figure out the new volume? Yes, I could. So this is called the combined gas law. And how do we get the combined gas law? By solving for PV over T. Now notice, using the combined gas law, okay, something very important. Something very important. The number of moles is staying constant. So all of these relations work, but you have to think that moles are always constant. Now, how do I know when to use this formula? Now, let me explain this a little bit. When you use the combined gas law, I'll just write this here, combined. I call it, okay, it's changing because it's Grodsky calling it. We're going to call this the dynamic equation. Why do I call it dynamic? Because I have a current situation. I have a current pressure, current volume, or temperature. What's the new volume if the pressure temperature changes? What's the new pressure if the volume and temperature? So this is, I call this, all right, current. I call this the future. So if you know the current conditions and the conditions change for the same gas, I can solve for one of the others. Things are changing. Notice we're going to have two pressures, two volumes. So you have two formulas. You have PV equals nRT. That is static. You use that when nothing is changing and you have moles, or solving for. Then you have PV over T equals PV over T, called the combined formula. I call that the dynamic formula. Why is it dynamic? Because things are changing. New pressure. You're going to have two volumes, two pressures, maybe two temperatures. Okay, current condition, new condition. All right, make sure if you're using the static one, you use the R and you're using 0.0821 with these units. And if you don't have these units, you're going to have to convert. And that's where the two gas laws. Regents land, okay, uses just this one. But they don't truly understand that that only works when what's constant? The moles are constant. So what I want you to do for the homework that I gave you, okay, for the 3 questions, I want you to figure out if you're using the ideal equation, okay, PV equals nRT, which is the static one, or are you using this equation to combine, and then try to solve for it, okay? Good luck. See you tomorrow. Rock on.